Basically, Hypothetical as the project is a KPL design, and then we are the overseas engineer, and we are working with local CCDI Design Institute as a normal practice in China. The building right now is slated to be 660 meters to the top of the cap, but right now. We're still trying to sort out the flight path situation. So right now, the building will be built at least up to 600 meters, and then we will have the spire ready for construction as long as we get the approval during the application process. I'm not going into statistics of this building so much. We have 5 levels of basement, basically almost 5 million square feet with the podium. The building is separated into 8 zones as normal. Why we have all the zones in China is because we have a refuge floor almost every 14 to 16 stories due to the building code. So this refuge floor is a good opportunity for structural engineers to put their structures to good use with this, and it divided the building into 9 zones. You can see the building shape, which is quite slender. It has to taper at the top in order to make it more aerodynamic. One thing I want to emphasize is all this tapering and the notches help us quite a lot with the wind tunnel test, having wind load reduction. The building is very simple, the floor plate. Before I go to the floor plate, you can see, even with this column pushing out a little bit, it is part of the wind tunnel test things in order to, and also this re-entrance corners, we really go through a great length with our WDI wind tunnel consultant to see how we can achieve both architectural advantage by making this notch in and out, and also creating more floor space in between in order to make the building suffer less from vortex shedding. But before we go to the other thing is you look at the floor element. One thing quite simple is the layout of the core. We have a very symmetrical core layout. We basically tic-tac-toe, 1, 2, 3 is a tic-tac-toe, 9 cells. Which we work out closely with the mechanical engineers. Once we have a very symmetrical core, it solves a lot of problems and makes things easy. And also, we try not to have a complicated core, because if the core becomes complicated, it will cause lateral problem. And we also try to line up the super columns, pretty much try to be in line with the flanges of the shear wall or the core. In order to minimize the 2 vector components, in order to make the outriggers much easier. As usual, for high-rise building, people will ask why. I will explain to you later why we have the X-bracing diagonal. There's a long history behind it. But not at the beginning, we do not anticipate to have exterior diagonal for the building. The building main lateral system is nothing but a core, a composite concrete core with steel plates and steel columns, working with outriggers, working with outrigger truss, and to form the lateral system. So basically, the core working with outriggers and the outrigger truss pass through the core and better than in order to have a defined load path. And then on top of it, we also have a virtual outrigger. We have a virtual outrigger. This around the perimeter of the building. This virtual outrigger is called the belt truss. It's the belt truss. The belt truss is supposed to pick up all these local gravity columns on each floor, so in order to transfer the load to the super column. At the same time, this belt truss will also work as our exterior mega frame which is a secondary redundant system for the seismic, which I'll go into a little later about what it will do. Why suddenly we have 2 layers of belt truss? Actually, we don't. Why you have to install 2 belt trusses instead of 1? It is the requirement at the end by the seismic review expert. They think that to have a space truss will give the building a better safety, because they see that if I have a single line of truss with a very long super column, they don't feel comfortable. Even we show all the tests, we can brace it here and there. They still recommend the building to have, because of this long super column, they have 2 lines of belt truss. So we basically divide the tonnage into 2 for better bracing. And also they think that they want to have more torsional resistance, because it is a box, okay? But so far the contractor overcome the construction difficulties. The green color is represent the diaphragm action, because normally we can depend on the concrete slab diaphragm action to take the horizontal shear, but the expert doesn't want to depend entirely on the concrete. Even we prove the beams and everything is okay, but they want to have independent load path for the diaphragm action. That's why we get all this horizontal bracing to satisfy to bring the load all the way into a clear load path. Another thing we want to look at, if you look at it, this plan, there's no corner column. There's no corner column. So if we have the cantilever, I don't know whether you can see another floor plan. If we have there's no corner column, okay. If we have this corner column, we have corner post. Because if we have this continuous corner column, this column will be very big. So the architect said, how do we make this corner column as small as possible? So we end up having a diagonal bracing outside in order to pick up this, to make this corner column work as a post only at every 15 story. So this is the reason why you have a smaller corner column. Okay, so basically, also at the same time, in China, they want us to have a secondary frame action. So basically, we moment connect the beams here in order to give them a continuity moment frame to satisfy the expert requirement. So we cover that. Okay, now, so basically the framing is quite simple. In order to make the building light, we have a composite steel beam with shear studs, and then we have concrete slab on metal deck. And as we say, basically this is the typical floor building of the building. Now this is the gravity framing. You can see why we're using double belt truss, and the depth of this belt truss, or you call it the metal frame girder outside, it has to be at the mechanical floor, but the depth, some of them will become one story deep or 2 story deep, depending on the mechanical requirement. And you can see this post, the corner column, we reduce it, the tiny post will be taken up by this corner bracing, the chevron bracing. Now, Shenzhen is better than Shanghai with the soil condition. We will be able to find weather granite instead of clay. So basically, we don't have to go that deep, even with the several level of basement. So basically, we still have a tile supported mat. It's a concrete mat on tiles, but we have hanger caissons, 16 huge hanger caissons under the core, working for us. And the big hanger caissons are underneath the super columns. And you can see the net foundation. This is the big hanger caisson, and we have a tile mat, the podium mat on tiles. And instead of a diaphragm wall, we have a secant wall. And you can see the huge hanger caisson. They can bear on the weather rock down below. It's much better than the Shanghai. We have much smaller settlement issues for this building. And this is the picture, you can see the big tender caisson and all the other smaller ore pipes. Again, we discussed it, the building is electrical systems, which is the core. Basically, we name it as Outrigger system and core with mega frame. But the mega frame is not that precise because of the other reason. I'll go to it later. Link beam is very important when we design high-rise, and this link beam couple all the shear walls together, and they have different requirements, whether you design for yield, design for elastic, and so on, under different seismic reasons. I'm not going into all the details of the design criteria for all the link beams and so on. And the super column. And the super column size are under scrutiny all the time. We try to use high strength concrete that can make the column size smaller, and then and also use enough steel, build up steel column to enhance it. The shape of the concrete column is a working product with the design architect KPF. This is our record. But the go fast, we covered already. This is a long one. Okay, here. Now, besides the outrigger and the core, we have this chevron bracing. One of the reasons is this corner column. So basically, we pick up this corner post and buy this chevron bracing. And also it fits into the KPF curtain wall design, because KPF design also have a curtain wall or configuration that can fit into it. At the end, we run the lateral analysis. You can see we have a deeper bell truss here. We have a shallower bell truss with a deeper one. When you run the exterior mega frame, we cannot meet the China code requirement, because the China code requirement said you need about almost 10% to 15% of exterior frame stiffness. And how do we get it? Because our core is already very stiff. Our outrigger truss is already stiff. They're taking most of the lateral load already, giving us most of the lateral stiffness for the building. And the reality is, this mega frame, this so-called mega frame, is giving us only 2 to 3%. So how do you get up to 10% or 15%? There's no way, unless we add more outrigger truss in order to make a huge moment frame. So after a lot of try and error, by trying and working with the expert, we come back and say, okay, the only way to do is put some diagonal bracing outside. And they want us to put diagonal bracing in a very dense manner. That's another big battle, or big working sessions with the local authority. What is really required for the exterior stiffness? So how can we fight the exterior? How can we humanly, artificially put so much stiffness to the outside? So it is not efficient. So eventually, we run through so many configurations, and also this diagonal outside is really disturbing the architectural design. And also, if this building is a apartment building, if this building is a hotel building, this will never work with the architect, because if you are the tenants of your apartment, you don't want to have a diagonal going through your windows, in front of your windows. Fortunately, this project is an office building, headquarters of Ping An, and like most of the exoskeleton building, you can see they are mostly office building. That is more accommodating with super diagonal. So even with the super diagonal, we can only put it in such a way between each zone is about 15 floors or 16 floors. So we do different configurations. And also when they bring the handle point together, you see, this is the handle point of your bracing, which is the corner diagonals to support your corner column. We try to match it and work in tandem with the architectural design. We come up with this yellow configuration. At the beginning, the expert wanted to put X. It's really very bad. Eventually, we go through different rounds of analysis. And also we have to do a performance-based design, which is the seismic. We did performance 3D we're using the abacus. Also, we're doing nonlinear dynamic analysis. All these things to prove to them that this, whatever it is only secondary. Without that, the building can still perform way satisfactory structurally. But still, they cannot relieve the rule. So at the end, we make some compromise with them to accept certain reduced percentage of the exterior frame stiffness. We still have some frame action, we're very minor, and also we have to design all these so-called mega frame for certain seismic base shear, which is still about 20% seismic base shear, and then we use different load factor that the seismic expert gave us to design. Every step as a structural engineer on this job, we have the responsibility to do something professionally. That means we cannot over-design anything. At the same time, we cannot under-design anything. So it becoming a back and forth working sessions with local authority. It takes us a lot of time. And we have to go back to talk to the owner and the architect why we're doing it. That's the challenging part of this project. It is unique. It's different from the Shanghai Tower. Shanghai Tower with another battle to deal with. How to come up with acceptable design criteria in order to have a simple building. So this is some of the side story we want to share with you. Each project is not necessarily that straightforward. I'm sure my colleagues, structural engineers, will experience the same thing. We still have to do a lot of extra work in order to overcome these code issues in China, but in a reasonable way and a professional way. But so far, the experts in China are willing to accept our analysis as long as you can prove to them that it is reasonable and it works. So far, we have very successful record to get approval on this super high-rise building. So you can call it chevron bracing, and we were so lucky that we find a solution that the architect can accept and the owner will accept. And we keep the chevron bracing size as small as possible. But one thing I'm not too happy with is at the beginning. So you can see this is some of the outriggers. And we locate this outrigger with different locations. Not every mechanical floors we need outriggers. Normally it's the rule of thumb, I would say, we cannot, if these are 9 zones or 8 zones, we cannot put outriggers into every zone. It is a waste of money and time. We don't need it. Normally, I mean, for a building like that, even every 1/3, 2/3, and top third is good enough. That's a rule of thumb. Of course, we do different try to adjust the location of the outriggers to see where it's necessary. But normally, I try with 1/3, 2/3, and the top third first. So this is a different location of the outriggers. We come back, we find that this is important because the building is tapering, and also the shear wall is giving us different stiffness inside because of different functions. So it's not that uniform. It's quite uniform here, but here we need it closer because of the shear wall situation. Now, you see, one thing I mentioned about the exterior bracing I'm not happy with. You see, I can compromise with this diagonal bracing, but I really hate this one, the X. Okay. Okay, so this is the one we battle hard and try very hard to get rid of because this is a lobby, the grand entrance. However, they insist to have this double bracing. So at the end, this is top of the podium. So somehow we work out a podium design with AKBF architect. They will accept this one because. This is not only the main podium entrance, because at the corner, when we free up the corner columns, we create another side, fantastic looking corner entrance. So the demand on the entrance appearance of that is not that much. So we are able to achieve this requirement for the expert. So ratio and all that. So this is another side story. So at the end, we call it a mega frame. It's not a moment frame. We call it chevron bracing. We call them mega frame as a secondary system for seismic requirement in China. You can see the shear wall is another thing. We try to make the shear wall layout and tape and drop off the shear wall and as it goes up in a uniform way. So at the end, we achieve a very simple solution. We did an extensive wind tunnel test because of the typhoon wind load in Hong Kong. And again, we go through the China code requirement and RWDI requirement. So these are all the statistics. The building perform very well. We do not need we do not need a 2-mass anchor. We achieve about 25 BDG criteria. However, to play safe, because during typhoon, I think the acceleration goes up to around 25.5 or 25.8. So it exceeded the something. But typhoon in the office building, many people will not work in the building. But for to enhance the human comfort and to play safe, the owner decided to do a 2-mass damper. And then I think nowadays, at the beginning, we have a double hung 2-mass damper as a passive damper, but right now the latest thing is going to be a active damper because of the space limitation at the top. We don't have, because the building tapers so much, we don't have enough room to host a passive damper with pendulum. So again, we do all kinds of modeling, like all the structural engineers will be doing. And we just, so far the building is symmetrical. We have building period by matching each other. And so far so good. And these are all these recessed corner I talked about, how we reduce wind load and all that. And we try different configuration of the corners. And this we definitely will do performance-based design. I think nowadays anyone who is designing high-rise building, we must do seismic nonlinear dynamic analysis. That takes us a lot of time, and you have to buy extra computers with enough license to run the 7 sets of curves and in XYZ direction, envelope them, and do all kinds of load factors. So this is quite demanding. And normally you get several jobs together in an office for high-rise. You're fighting for license. Now, material, we meet all the LEED requirements, so we try to do recycled material, fly ash, and concrete, high-strength concrete. So anything we can structurally to use recycled material, we use. This is the picture you have seen in the morning, and all this is a big hand-up case on bearing on where the rock below. So this is a panel test and so on. So again, one thing I'm not happy with this is obviously the X-bracing, which we cannot get rid of. But before, you can see it's very less intrusive. So far, it's not intrusive at all. But at least it gives something back to the expert requirement for redundancy. Thank you.